So in the clustering R exercise for clustering, since it's our first time doing clustering, so I thought we need to go through this. We use a whole set of libraries. And I noted here, why do we need any of those? Next week, I think we're going to look at this t-SNE video. So I'm going to skip t-SNE video. t-SNE is a visualization method that allow you to visualize multi-dimensional data in a two-dimensional or lower dimensional, just 1 and 2 dimensional space that you can actually view. The idea is to preserve the relative difference of the data, relative distance among data points in higher dimension. In clustering analysis, it can be used for you to observe the clustering tendency of the data. We can video that you can probably watch on your own, or we can watch it next time. But the idea is to for you to look at data in lower dimensional space. I'm going to use the iris data first to illustrate the random data. How does that going to look like versus the data with clustering tendency? So we use the iris. We remove duplicates. t-SNE requires distinct observations. We remove species was the label, remember? So we want to remove the label. We look at the data itself. So with this cleaned up data frame, I created a random set of data that fits the iris data's data frame. The goal is to compare data with clustering tendency versus random data. So I used the random method to generate uniform set of data. We're going to generate for each every column. We use apply function. For each every column, we're going to generate the number of data in that column with the minimum and the maximum that presented in that column. So this is our random data frame. We make it a data frame. Then we scale this, as remember, because t-SNE use distance, and we need to scale this to data set using the z-score scaling. Then I set seeds. Once you watch the t-SNE video, this is really a very fun video to watch. I highly encourage you to watch that. It will tell you a lot of things about, you know, to what extent we can trust the t-SNE visualization. So we have, so we're using this DF data frame. This is the petal length and the sepal length data. So it's not a distance matrix. Perplexity is one of the parameters that t-SNE requires. We will use the default value. The default value works pretty well. So from this number, from our data set, we use t-SNE method to generate a t-SNE object. And then the t-SNE, we can look at the thing that's outputted. t-SNE $y give you the new values for a pair. For every data points, you have a pair of values that you can plot in a two-dimensional space. I think earlier our data was 4-dimensional, and now we have reduced it to 2-dimension, and the relative distance among those data points are preserved. So what we did here is we pass it along, make it data frame, then we give it name, X and Y for the columns. Then we add our the iris species as the cluster name, so we know which data points belongs to which species in the original iris data set. After we did that, we can actually ggplot. So this shows clear clustering tendency. We can see this is a cluster. These two clusters may overlap with each other, but we can still see those are very clear clusters. In contrast, we can use the random data set that we just created. We run this. We do the same thing. We do plot. This is random. We can see even after t-SNE trying to get the data into its closest, it preserves the relative closeness of those data points. And those data points are just randomly scattered around. The Hopkins method, let's see how much time I have. I have 2 minutes. That's probably enough for us to do the Hopkins. Hopkins for numerical data only. So we used 2 different libraries. They gave us different, one is 1 - h. Remember, I talked about that earlier. So I think this one computes the h. So we used our DF, get cluster tendency. This gave you the Hopkins statistics. So we do that, look at the Hopkins. We have a score which is greater than 0.75, so we know that it's highly, it presents clustering tendency. When we do the plot shows this way. We can see very clearly at least 2 big clusters. So this is how we're going to look at the sort of a data matrix type of visualization. That you can see similar, that the data is grouped, that they similar points are clustered, similar colors are close by. On the random data set, we could do the same. We run the Hopkins stats. The result is very close to 0.5. If we do a plot, what you're going to see is something like this. Compare this to, you can see the second plot is very much random. Have purple and orange dots everywhere. The other library we used is clustered, clusterand. This again, this one gave you, even though the method is called Hopkins, it gave you 1 - Hopkins. The score is 1 - Hopkins. So if we run this, it will give us a H score, which is pretty much 20%. Earlier we have 80%, right? So on the random data, you're going to have a very high score. I mean, a score close to 50. Okay.